Okay, welcome back to EE210B. We are going to continue our discussions of information processing over networks. In the last lecture, we discussed centralized processing, if you remember, and we compared the performance of centralized solutions to single agent solutions, right? So today we are going to start part 4 of the course, which deals with processing over networks. Okay, so today we will start to study deeper inference over networks. This lecture in particular is going to introduce the network model for you. So we need to understand what is the network model, what properties it has, so that later when we introduce algorithms to solve adaptation, optimization, and learning problems over these networks, we're going to exploit these network properties to prove convergence results, performance results, and so forth. Okay? So, this is part 4 of the course, which is the part where we start to talk about multi-agent networks. Today, in particular, we are going to talk about network models. Okay? So, the reference for this particular lecture is chapter 6 from the text that we are using. He has it over there. Okay? And there is also an appendix A from this survey chapter I wrote. I will use some of the material from there. Both of them, you can download them from my website. Okay, so the references are available on my website. Very good. So like I mentioned, the purpose of the coming lectures is to study distributed strategies to solve adaptation, optimization, and learning problems over networks. In preparation for these studies, I need to explain to you what is the network model that we will be using and why we use the model that we will be using. Okay, so that's what we are going to do today, introduce the network model. Okay, so let's first define what are connected networks. So I'm going to define connected networks, weakly connected networks, strongly connected networks, and then until the end of the lecture, of the class, you will only hear me talk about strongly connected networks. That third type of networks is what we focus on for the reasons I'm going to explain. But I need to introduce the other two so that you understand why we don't focus that often on the other two, okay? So like I say here, okay, so we are going to focus on connected networks. Loosely speaking, a network, I'm going to define it more formally, consists of n agents, n nodes, linked by edges, right? Linked by edges. If you pick any two arbitrary nodes in this network and you can find a path linking them, then we say it's a connected network, right? So it just means what it says. That's what a connected network is. I'm going to define it more formally. For us, because we will be dealing with weighted graphs, so when I say a connected network, it means something a little bit more specific than what I just said. Okay? On the face of it, that's what it means. Pick any two agents. If you can find a series of edges connecting them, that's a connected network, but I will be more specific very soon. Okay? So the topology of a network, to describe the topology of a network, okay, we will talk in terms of graphs, vertices, and edges. You have vertices or nodes, edges connecting them, and the resulting structure is a graph. Okay? So this is a more formal definition. So a network of size n consists of n vertices. In this course, I will be using more often the term agent or node, right? Because these vertices will be doing something, so we often use more the term agents. So I have n vertices, right? You will have n vertices, n of them, and then you will have edges connecting some of these vertices to each other, right? These are called edges. Sometimes you will have a self loop, so that's a particular edge. It connects a node to itself. Okay, a node to itself. Because as you are going to see, when you are solving an adaptation problem or a learning problem, you collect data. And you also observe the data from your neighbors. To get the data from your neighbors to your place, you are going to use the edge that connects you to your neighbors. So the edge connecting you to your neighbors is useful because you can exchange information with your neighbors through these edges. The self loop is to mean that you also are going to use the information that you collect at your location. That's the self loop is is useful to represent that dynamics, okay? That the information that's present at your location, you're also going to use it in your processing, okay? Very good. So this is one representation of a network. I have n agents. So here I'm focusing on a particular agent, agent K here, okay? And this agent K is connected to how many other agents? L is 1, 7, 4, and 4, right? So it has 3 neighbors besides itself. We consider that every agent is a neighbor of itself. Because by neighbor we mean an agent with whom you can share information. So technically an agent can share information with itself. It has access to its own data, right? So the neighborhood of node K in this case consists of the agents with which it has edges, okay? So it will be L, 4, 7, and K itself. Even if there is no self loop, we consider K to belong to the neighborhood of agent K, okay? So the dotted line that you see here, is representing the neighborhood of node K. So this node has 4 neighbors, L, K, 7, and 4. Fine? Number 1. Number 2, in this diagram, which is a little bit cluttered on purpose, it will become simpler as we move, I'm representing the edge between any 2 agents by using 2 arrows. We are not going to do that moving forward, but for now I want to make it explicit that actually the edge, if this is L and this is K, and you have an edge connecting them, that edge actually is telling you, because we are going to assume that the graph is unidirectional, that the agents can share information in both ways. Okay, so that's why I'm making it explicit for now. If I have L and I have K, L can send information to K, and K can send information to L. Right? So that's why I'm being explicit, that this edge actually is behaving like this. Okay, it doesn't mean that the exchange of information is symmetrical, because over this edge, I'm going to assign 2 weights, which I call them A from L to K, A from K to L. Okay, so that's how I read these subscripts. The first subscript is the source, where information is coming from. The second subscript is the sink, where information is going, okay, from K to L, from L to K, start, end, okay? So that's what you see here, right? On the arrow that goes from K to L, there will be some weight from K to L. This is a non-negative number. And on the arrow arriving at K, there will be some other weight. Okay? These weights will be used, as you're going to see. For now, I'm just introducing the model. These weights are going to be used by nodes to scale the information that they receive from their neighbors. So, for example, if he's L and I'm K, and he's sending me information, and I don't trust his information, I can set ALK to 0, right? Okay? If I have 2 neighbors and I trust you both equally, I can give you 1/2 and 1/2 weight, right? So these weights, later we are going even to adapt these weights. But for now, let's think of them as some static weights that exist all over the network. And the exchange of information between L and K doesn't need to be symmetrical, because I can trust L more than L trusts me, right? So these weights don't need to be equal values, right? But they exist. One of them can be 0, the other doesn't need to be 0. Both of them can be 0. So you see, from the perspective of adaptation, learning, and optimization, this is where there is a distinction between what we are doing here and pure graph theory. Okay? From the perspective of adaptation, learning, and optimization, even if I have an edge connecting 2 agents, there may be no information exchange on that edge if they set their A's to 0, for example, right? Okay? And there may be information going only in one way and not in the other way, right? And the exchange of information may be weighted differently in both ways. So this becomes a weighted graph, okay? We are going to weigh information by these coefficients. And then what you have here, you have a self loop. This is an example of a self loop. In this case, 2 is going to weigh the data it receives from itself by some constant, A22, right? Yeah. I'm coming there. Okay, for now, they are non-negative. The next slide will expand on this, okay? For now, they are non-negative weights. Okay, so you understand the network model, the concept of a neighborhood. So the notation I use for the neighborhood of a node is like this, N sub K. Okay, neighborhood of node K. Okay? So I'm coming to your question. Okay, so for now, I said that the graph is undirected, meaning that information can flow on an edge in both directions. If K is neighbor of L, L is neighbor of K. Okay, and if we are neighbors, it doesn't necessarily mean that we are sharing information, because the A's can be 0. It doesn't necessarily mean that both of us are getting information from each other. Just keep that in mind, because this is important for the context that we will be discussing. Okay, and then here, any two neighbors can share information over the edge, right? But this doesn't mean that the flow of information is symmetrical, right? Exactly what I just told you. Okay, so here I'm just defining the weights. Okay, from K to L, L to K, and you end up with a weighted graph. Okay, so these slides are just repeating what I said. Okay, and the figure I explained to you. Okay, so now let's come back to these weights. So the neighborhood I already defined. Okay, so the neighborhood of an agent K I denoted by this notation, N sub K, and it consists of all the agents that have edges connecting them to K, right? Okay. And the neighborhood includes agent K itself. Fine? And if I am your neighbor, it means that there is an edge connecting us, and there is the possibility of sharing information over that edge. Whether we want to share or not, that will depend on the problem that you are solving, right? And on what weights you assign to these edges. Okay. Now, so what do we mean by a connected network? I'm going to be defining it very soon. If I go back to this graph, remember that I mentioned to you before that a connected network is one. I give you a graph, pick any two neighbors, any two agents, nodes, you can find a path linking them. Actually, I will be a little bit more explicit. To us, we're not only interested in the graph aspect of the problem. We are interested in exchanging information over the graph, because we want to solve an adaptive learning problem and optimization problem. So these agents will be sharing information over this graph, right? So technically, even though there is an edge between K and L, if both of these weights are 0, for all practical purposes, there is no exchange of information over that link, right? Even though it looks connected, but there is no exchange of information. So the more specific definition that we are going to use to refer to connected networks is this. The network is connected if for any two agents, you can find a path of non-zero weights linking them in both directions. Okay, so for example, L and 7. I can find a path that goes from L to K, from K to 7 with non-zero weights here and there, right? And to go, for example, from the paths do not need to be the same. To go from 7 to L, let's say I can go that way instead. Okay? As long as you can find a path that takes you from one node to the other through non-zero weights, and as long as you can find a similar path that takes you back, then we say the network is connected from the perspective of sharing information over the network, right? From that perspective, we call the network connected. You understand the difference? Okay. That's what a connected network is. A weakly connected network, which we will not be studying, but it's useful for you to know the difference. A weakly connected network to us is a network where if you pick any two nodes, you can find a path at least in one direction. And by path, I always mean a path with non-zero weights, a path where you can share information, not just an edge, right? So if there is a path that can take you from L to 7, right, between any two agents, and I'm not requiring a return path, then that's weakly connected, because you can only share information in one direction between agents, not necessarily in the other direction. You understand? For a connected network, information from L can reach 7, and information from 7 can reach L. For a weakly connected network, information can flow only in one direction between agents, at least, right? So you may not have a return path from 7 to L. So 7 can see what L is getting, but L cannot see what 7 is getting, right? So we call it weakly connected. You understand the differences? What is a strongly connected network? Strongly connected, and that will be the kind of network we'll be talking about. I will not be talking anymore about weakly connected or connected, maybe only in the homework problems. But for the lectures, we'll focus mostly on strongly connected. What is a strongly connected network? First, it is connected. So pick any two agents, you can find a path going forward and coming backward. And in addition, there is at least one self-loop. At least one person, one agent in that network trusts its data. At least one, right? Okay? Because it would be very strange if no agent has a self-loop. It means that they don't really trust their own data. Okay? You understand what a strongly connected network is? Very good. So these are the definitions that I have here. I defined what a weakly connected network is. Between any two vertices or agents, you can find a path that goes at least in one direction. So information can at least flow in one direction. Okay? This is a weakly connected network. A connected network, you can find paths that flow in both directions. They don't need to be the same path, but you can go from L to 7, 7 to L for any other pair of agents. And strongly connected, in addition to being connected, at least one agent K has a self-loop. Fine? You understand the definition? So you see there is a subtle difference between strongly connected and weakly connected networks. Let's look at this example. Look first at the network on the left. Okay? If you pick any two agents, let's say pick two agents, arbitrary two. 6 and 4, okay? So I can go from 6 to 4, how? 6, 1, 2, 3, 4. And I can go from 4 to 6, how? 4 to 5, 5 to 6. If you repeat this for any two other agents, you'll find that this is always possible. And there is a self-loop. So this is a strongly connected network. Information can flow from any node to any other node, and at least one node trusts itself. What I did here, this network is very much like that one. I only reversed one arrow. The one that goes from 1 to 2. I reversed it. It is from 2 to 1 now. This becomes weakly connected. Okay? Weakly connected. Well, you can see it. For example, look at agent 2. Information only goes out of 2 now. Information cannot arrive at 2. So if you pick any agent 6, you can find a path from 2 to 6. Let's say 2, 3, 4, 5, 6. But you cannot find a path that goes back to 2. So 2 in that case is only feeding information. 1 in this case is only receiving information. So from a network perspective, if you are solving an optimization or an adaptation or learning problem over this network, these agents are not going to benefit from information that one sees, because one doesn't send information to the network, only receives, right? And 2 is not going to benefit from the information they see, right? So over a network like this, not everybody is going to benefit from working together, right? That's not the case here. Even if you are not directly connected, you will be able to see the information or sense information that the other node sees, because ultimately that information is going to flow through the network and reach that point. You understand the difference? Okay. So now you understand what a strongly connected network is. Okay. So this is referring to the figure I just described. Okay. Very good. So what's so special about strongly connected networks and why we are going to study them? Right? Again, this slide is stating what I just said. Over strongly connected networks or over connected networks, observe that I'm defining connectivity not in terms of whether the graph is connected or not, but in terms of whether I can have meaningful exchange of information between the agents. So there should be edges, but they should be weighted by positive weights, right? You should not kill them. Okay, so that's a subtle difference that I would like to keep in mind, because for us, we would like to do information processing over networks. So there should be a way to share information over that network. It's not enough to have an edge, right? That edge has to have a positive weight on it. Okay, so that's one point I would like to make, that connectivity for us means the topology allows for the meaningful exchange of information. Fine? Number one, okay, and it makes sense, okay? Very good. So all scaling weights on a path must be positive, right? That's what we need, okay? And this is just expanding that a little bit more, okay? If there is any particular agent L0 that doesn't receive information from other agents or doesn't feed information to other agents, for all practical purposes, that agent is away from the network structure, right? It will not benefit from that structure, okay? So this is what this slide is saying, okay, in this text that you have there, okay? That sometimes information is never able to arrive at some agent, okay? Because the scaling is eliminating the edges that reach L0, okay? So you understand that. And information, okay? Now, why do we require strongly connected networks? Or first of all, we require connected networks so that information can flow both ways, right? Both ways. And we require strongly connected networks because then at least one agent trusts its data. And not only that, actually the condition of a strongly connected network induces some very useful structure, okay, on the graph, which we are going to exploit extensively, and this lecture is going to explain to you what this structure is. And then in the future lectures, you are going to see how this structure is very useful, okay? Okay. So what I want you to understand from this first part of the lecture is that strong connectivity is very useful because it enables the exchange of information back and forth, and at least one agent trusts its data, right? Okay, very good. So this is what we are saying here. If AKK is 0 for all agents, then all agents will be ignoring their individual information, right? And will be relying instead on information from other agents. That's what will happen if this is the case, okay? Which, okay, strongly connected networks do not satisfy. Now, the terminology strongly connected network, and I say it may be or may convey, right, may be excessive. Because if you tell someone that your network is strongly connected, they may get the impression that you are asking it to be overly connected, right, or almost fully connected, but that's not what it means. The network can be very, 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 very sparse. Let's say you have 10,000 nodes, right? It can be very, very sparse. And only one self-loop, it becomes strongly connected, right? So the terminology may be a little bit excessive, but that's what is used, okay? But I want you to understand that. By strongly connected networks can be very, very sparse. You understand that, okay? Yes.
Before applying these algorithms, we have to check that a graph that we have is strongly connected.
I'm coming there. Just be patient. Okay? 2-0. So you ask 2 questions, and the answers are coming, right? Okay? Good question, but it's coming. Now, so what properties strongly connected graphs have, right? To get to your questions, right? Here I'll answer the first question about convexity of these coefficients, okay? Now, you see, let's go to the figure. It's easier to explain it in the figure. Here I have a figure. I have a strongly connected network, fine? Zoom on an agent in that network, agent K. It has neighbors. So I'm only zooming on the neighbors of agent K here. It has 7, L, 2, and 6, fine? Okay. And I'm only zooming on the arrows arriving at K because I'm only interested in what's happening at K now, right? So K will be receiving data from each one of these agents, right? And the weights from 2 to K, from L to K, from 7 to K, from 6 to K. Okay, so we will be imposing the condition, this is the answer to your first question, that these are convex combination weights. Okay, so if I have 4 neighbors, I'm going, let's say, to give weight 1/4. Let's say I'm one neighbor as well, so we have 5. So I'm going to give weight 1/5, 1/5. This is one option, right? The weights do not need to be uniform, right? But they add up to 1 and they are non-negative. Or I can give non-uniform weights. I trust her data more than hers, and so forth, right? So like you said before, these weights have to add up to 1, okay? So if I want to write this, so these are the weights that arrive at node K, you see, from any node M in the neighborhood of K, this should be 1, right? That's what this means. These are all the nodes from any node M in the neighborhood of K arriving at K, they should add up to 1. This will be our assumption, right?
Does that include the self loop?
Yes, self loop. I said that the neighborhood, right? The neighborhood includes the node by definition, okay? AKK can be 0. It can be 0, right? But it's included in that definition. Now, let's represent this in matrix form. Matrix form. So I have a network which has n agents, right? N agents. So I'm going to define a matrix A. This will be a very important matrix for us, called the combination matrix. You have a network. You have n agents and edges connecting these agents, and you'll have weights on these edges. You can take all of that and connect it, represent it in matrix form. How? Like this, okay? So let's look at this. So this is a column which has, a matrix which has n columns, and it has n rows, okay? So let's pick a particular column. The column corresponding to agent K, right? You have n of them. Column corresponding to agent K. So agent K has how many neighbors? 5 neighbors in this example, right? Okay, neighbor 2, so this is row 2, and then row 6, row 7, and row L, right? So at locations 2K, 6K, 7K, right? This is Kth column, right? K is a column index here. Those A's will appear there. All the other entries on that column will be 0, right? So if you look at a particular column in this matrix, it tells you for that agent, which other agents are connected to it, and what are the weights, right? And all the other entries will be 0, right? And this column, if you add its entries, what do you get? 1, right? You go to agent L. Now, agent L will have neighbors, right? I'm not showing it in this figure, but one of them is K, right? So in the Kth row, you will get the A from K to L, right? L is the column index now, right? So this is what the matrix does, right? It collects all the weights across your network. So by looking at this A, you can figure out what the topology is and what the weights are, right? Who is connected to who, and what the links are. Understood? Okay. So we are going to represent the network by this combination matrix A. This is a very important matrix because it doesn't only reflect the graph, it also reflects the weights on the edges in this graph. And if some AKK are non-zero, it will appear on the diagonal here, right? AKK somewhere will appear, okay? Very good. So this is called the combination matrix, okay? Because this contains the coefficients that agents will be using, as you're going to see in future lectures, to combine data, okay, from the other agents. Okay. So what are the properties of this matrix? Okay. So before I continue, first of all, each column adds up to 1, right? So the way we represent it is by saying this, okay? Each column, so A transpose times the vector of all ones, what do you get? The vector of all ones, right? This notation is for the vector that all is, right? So if you transpose the matrix, a column becomes a row in a product with the vector of, right? Okay, so this combination matrix has this property, always. And the entries are non-negative, right? Okay. This tells you that the vector of ones is an eigenvector for A transpose, right? With eigenvalue 1, right? Because we will be using this a lot. Okay, but it's trivial from here. Fine? And matrices with non-negative entries, right? Like probability measures, that satisfy this condition, the columns that add up to 1 are called left stochastic matrices. Left stochastic matrices, left stochastic. Okay, we talked about this when we reviewed matrix theory early on in the course, right? That's the definition. If the columns add up to 1, they are called left stochastic. There are matrices that are called right stochastic. We are not going to be using them here, but just so that you know what it is, if the rows of the matrix add up to 1, then it's called right stochastic. This is not the case here, right? If each column adds up to 1 and each row adds up to 1, if both of these conditions are satisfied, and you will see matrices like that later, Okay, it's called doubly stochastic, doubly because of the rows and the columns. Okay, this is the terminology. For us, the most common situation would be left stochastic or doubly stochastic, both of them together. Okay, and the left stochastic comes up simply from the convex combination condition that you mentioned, right? Okay. Now, what's so special about this matrix A for strongly connected? The fact that A represents a strongly connected network imposes some structure on A, which I'm going to explain. And this structure will be very important when we do our analysis, okay? First of all, you understand that in general, graphs are sparse. They are not fully connected like what we did in the last lecture on centralized solutions. That's the purpose of showing that the processing over sparse graphs will attain the same performance as centralized solutions. That's what ultimately we are going to get to, right? Okay, so in general, this A will have many zeros in it, correct? Okay, many zeros in it. Entries are non-negative, columns add up to 1, and it has many zeros, okay? However, okay, if your graph is strongly connected, I'm going to prove this result. It's important for you to understand it. If the graph is strongly connected, it will have the following property. Even though most of the entries in A are 0, you can find some power. You can find some integer n, such that all the entries of this power of A will be strictly positive. All of them will be strictly positive. Understood? Okay? So let's look at that. Okay? So here, and matrices, by the way, left stochastic matrices that satisfy this property, for which you can find the power, and I'm going to tell you what's the implication of this very soon. For now, I'm just introducing the property, okay? Left stochastic matrices that satisfy this property are called primitive matrices. Primitive matrices. So what this is saying is that combination matrices of strongly connected networks are primitive matrices. That's all this is saying, okay? So this is, okay? This is the statement of the lemma. The combination matrix of every strongly connected network is a primitive matrix. Why primitive matrices are important, you are going to understand it very soon, okay? But for now, let's prove this result, okay? Okay, so this is some algebra here that I need to follow to prove the result, okay? It's important that you understand why this is true, okay? So I want to show that the combination matrix of a strongly connected network is primitive, right? Okay. Means I need to be able to find a power such that A to that power will have all positive entries, okay? So this is how we prove it. The proof is not difficult, but it requires some argument. Pick any two arbitrary agents, L and K. Since the network is connected, because it is strongly connected, I can find a path of non-zero weights going from L to K, right? So that's what I wrote here in equation 6.2. Starting from L, going to K, I can find some intermediate agents. I don't know what they are, but they exist. And weights, for example, from L to M1, from M1 to M2, right? This is what this notation means, right? The notation looks difficult, but it is simple. Some intermediate node, I'm calling it M1. So this A will take you from L to M1. And then some other node M2. And this weight is what takes you from M1 to M2. And some final node here. Okay, so this path I'm saying has length, because the agents are LK, I'm calling the length of the path N with subscript LK, just to attach it that I'm talking about these two particular agents, right? For some other agents, the length could be different, right? Okay, so you have N LK of these nodes. I don't care what they are, but they exist. And the weights here are positive by definition, right? Okay. Very good. So now, if I take this matrix A, and I compute that particular power, let's say this path is of size 3. So I compute the third power of A, okay? And I look at the LKth entry of that, okay? From the definition of the matrix multiplication, it's not difficult for you to find that if you multiply a matrix this many times by itself, the LK entry will be given by this multiple sum that you have here, okay? So this is A that goes from L, this is the A at location LM1, then M1, M2. This product here, if you add it over all possible m's, this sum is the LK entry of that power of A, right? This is just from the rules of multiplication, okay? If you don't believe me, just do it for A squared and you will see that, okay? This is just, okay? But now, because the network is connected, we know that this product is positive. We know that there exists at least one combination of M1, M2, right? That will give you positive here. All the others could be zero, but there is at least one of them for which the product is positive. Therefore, this quantity here is positive, correct? Okay. So what have we shown so far? What we have shown so far is if your network is strongly connected, if you pick any two nodes, you can find a power of A such that that particular entry of that power is positive, right? This is not what we want to show. This is much weaker than what we want to show, right? But still, you know, this is called an irreducible matrix. This kind of matrices is called an irreducible matrix. If you have a matrix, in this case, a left stochastic matrix, such that for every entry of that matrix, you can find a power that makes that entry positive, this is called an irreducible matrix. You understand? This is just a matrix definition, okay? If you have a left stochastic matrix like here, and for each entry LK, you can find a power. So these powers could be different. But if you can find a power such that the LK entry comes out positive, we say this matrix is irreducible. So what we have shown so far is that if your network is strongly connected, A is irreducible, right? We don't know what the implication of that yet is, but for now we prove this fact, right? But I want to show something more, right? What I want to show is that I can find a power independent of LK such that that power has positive entries for any LK, right? This is a stronger statement. That's what we want to show. This is a first step in that direction, okay? So this is called an irreducible matrix, okay? If for every LK, you can find a power possibly dependent on LK that makes this entry positive, okay? This is what we have shown so far, okay? Very good. Therefore, network connectivity ensures irreducibility of A. That's all we showed so far, okay? But actually more holds, and then I will tell you what does this property mean, okay? So because the network is strongly connected, more than that holds. I can find a common N0 that makes all entries LK positive for that power of A. Okay, so this is a stronger property that makes A primitive, okay? So let's prove that. Okay, let's prove that. The argument is simple, but it requires some algebra. Okay, so if the network is strongly connected, right, we know by definition at least one node, call it K0, has a self-loop, right? At least one node has a self-loop. Okay, very good. Now, I know from the argument I just showed you that A is irreducible, right? So if I compute the LK0 entry, right? Because it is connected, there is a path taking me from L to K0 for any L, right? And there is a power that makes this entry positive. I know that, right? Let's compute the next power. You see, just add 1. From the rules of matrix multiplication, if you just add 1, you are computing the LK0 entry of this product, right? A times that. From the rules of matrix multiplication, okay, you are adding over all M the entries of this first matrix times the entries of this second matrix, right? This is just rules of matrix multiplication. Of course, this sum, because all entries are non-negative by definition, is larger than or equal to the one that you get when you set M equals to K0, because it's one of the entries in this sum, right? And we know that this is positive, and we know that this is positive. Therefore, this is positive, right? So what this argument is showing, because your network is strongly connected, if A is irreducible, which means you can find a power for every LK, all subsequent powers will also satisfy a similar condition, right? Because of strong connectivity, if your A is irreducible, meaning you can find a power that makes this positive, all subsequent powers will also be positive, right? Okay. So let's put these things together now, okay? So now, let's pick the largest n, okay? So here you see K0 is a node that have a self loop, right? And then for any other L, I can find a power of A that makes that entry positive. If I go to some other L, I can find another power of A that makes that entry positive, right? For any L that you pick, there is an L as n associated with it that makes that power of A positive. Let's pick the largest of these n's, right? Because of this property that if you increase the power, it stays positive, right? So if I pick the largest of these n's, that power of A will stay positive for any L. Did you understand this? Okay, okay? Because you see, pick an L. For this L K0, there is an n. A to that n is positive, right? The entries are positive. If you keep increasing the power until you reach the maximum m, it will still be positive, right? You see? So now, for this m0, this is a common m0 now, such that for any L you pick, all the entries on the Lth row will be positive. You understand where this comes from? Okay? Because, you see, let's assume I only have two L's. This is one L, let's say, with a path of length 2, and this is another L with a path of length 3, right? What this said is that the entries A squared between L and K0 is positive, and the cube, this other L prime K0, is positive, right? Because this is L and this is L prime 3 and 2 here, right? Okay, so now if I pick so this is one n, this is the other n. So pick your m to be the maximum among them, 3, right? So obviously, A to the m for L prime K0 will be positive because m is still 3, right? And likewise, A to the m LK0 with L will also be positive because of this property here. If you increase the power, it will stay positive, right? Okay, so that's why I can pick the largest n, and then this property will hold for any L, right? Okay. So what does this mean? Look what this means. This is a matrix. This is a matrix, A to the m0, okay? If L is changing, okay, so this K0 is a column here. This is K0. What this is saying, if you look at any entry in that column, for this matrix, they will be positive, right? I don't know about the other entries. But if I look at all the entries on that column of this power of A, they will be positive. Fine so far? Okay. Now, look here. The argument was, if your network is strongly connected, I can find a K0 where A is positive, and then I can look at all the passes that go from any L to K0, right? This is what I did, right? To conclude that the kth column of M0 has only positive entries. I don't know about the other entries, but that kth column is always positive. I can now reverse the argument. I can say if the network is strongly connected, there is a K0. Let's now look at all the passes from K0 to L rather than from L to K0. Just reverse it now, okay? The same argument. So let's now look at all the passes, right? So here there is a typo, okay? Just like here, I have K0. Okay, so this should be K0 here and K0 there, okay? Typo. You understand the argument, right? So now I switched. So from K0 to L, there is a power NK0L, right, of A. Then again, if you increase the power, the same thing will hold. Now pick the largest of these NK0L, call it M prime, I called it M there, call it M prime now. Okay? So pick the largest of them. Because remember, this largest value is finite because this is what? The length of the path between any two nodes. It can never be larger than the number of nodes. So this is a finite number, okay? So now, a similar argument then shows that for this power of A, all the entry on the K0 row of A, this power, are positive, right? So if you put these things together, we get the result that we want, you see? Let's now take N0, which is the sum of these two values that I found, okay? M0 and M0 prime. So if you look at this power of A, which is this A times that A, one of the A's has positive entries on the K0 column. The other A has positive entries on the K0 row. I don't know anything about the other entries. They could all of them be 0. But when you multiply these two matrices together, all the entries of A to the N0 will be strictly positive. You can see it, right? Because when you multiply, let's say, the first row by the first column, the plus will multiply the plus. You will always get a plus, right? A positive. And the same way for all other entries of A to the N0. You understood? Okay. So this proves it. Okay, so what did we prove? If your network is strongly connected, you can find a power of A, a finite number, N0. You can find it, right? If I give you an example, then you can work out and find it. You can find but this is a general proof, right? For a generic A, that there exists an N0, okay? Such that all the entries of this power of A are strictly positive. So this means that A is primitive, okay? So I proved that result, fine? So why this is important? Okay, you followed the proof? Okay. Because of this very famous theorem, okay, in matrix theory or linear algebra, which applies to primitive matrices. And you are going to see, if you follow these lectures, how important this result is in establishing stability, in establishing performance results for networks, and many other properties over networks will be based on this fact here. We will exploit this fact extensively. That's why I wanted to prove it, okay? What this theorem says is, of course, the theorem is more general than what you have here. I'm only stating that part of the theorem which applies to our work, okay? What the theorem says, okay? And again, I mentioned this theorem before when we reviewed matrix theory results for this course, right? And you have it in one of the appendices in the text, okay? If your matrix A is primitive, okay, so it has non-negative entries. In our case, it's also left stochastic. The columns add up to 1. So it has non-negative entries, and there is a power that makes all entries positive. So if your matrix is primitive, okay, it will have a single value at 1. All other eigenvalues will be strictly inside the unit circle. Okay, it will have a single eigenvalue at 1. All other eigenvalues will be strictly inside the unit circle. Fine? This is so a single eigenvalue, not even multiplicity. Okay? And importantly, of course, with every eigenvalue, there is infinitely many eigenvectors, but you can normalize the scale the eigenvectors, right? So let's call the eigenvector P that's associated, let's call the eigenvector that's associated with the eigenvalue at 1, let's call it P. And I normalize its entries to add up to 1. I can do that. I can scale it or normal. So this is what this condition is saying, right? I can always do that. Normalize the entries of the eigenvector to add up to 1. What the Perron-Frobenius theorem asserts again is that all the entries of P will be strictly positive. Strictly positive. You understand? This is not true for any matrix, right? If I give you any matrix has an eigenvalue and 1, you find its eigenvector, some entries will be negative, other entries will be positive, right? But what the theorem says is that if your matrix is primitive, there is, I call this the Perron eigenvector, okay? So because we'll use it extensively, so this is called the Perron eigenvector. It is the eigenvector that corresponds to the eigenvalue at 1. Entries normalized to 1, all entries positive by the theorem. And this is true only because the matrix is primitive. It wouldn't be true in general, okay? Now, this vector will be extremely important when we study networks. The performance of the network and the features of the topology that influence performance, they will all be represented by this vector. Okay? Now, because the entries of P add up to 1 and they are positive, its entries play a role similar to a probability measure, right? They are all positive, add up to 1, number 1. Number 2, you're going to see that these entries P reflect how important a node is in the network. Because how many of these P's I have? N, right? I have N. Each one of these P's you can associate it with the corresponding agent in the network because you number the agents here from 1 to N. Okay? Each one of these P's will tell you how relevant is the information in that network, at that agent's location, to the entire network. So this is a reflection of how important your agent is. Okay? Now, P is the right eigenvector of A, right? You already know a left eigenvector of A. Remember that A transpose 1 equals 1, right? So I can write this as 1 transpose A equals 1 transpose, right? So P is the right eigenvector, 1 is the left eigenvector. Fine? Okay. Now, if your matrix is doubly stochastic, sometimes our A will be doubly stochastic. For example, a left stochastic matrix that's symmetric will be doubly stochastic because then columns will add up to 1 and rows will add up to 1. If your A happens to be doubly stochastic, what would P be?
1
No? 1 over N, right? Because you have to scale them to add up to 1, right? Okay? You understand why, right? It is 1, but you scale the entries by N, right? So all agents will be equally important in that case, okay? Now, this statement, of course, you will only understand it more fully when you see the analysis that comes down the road, right? For now, I'm just stating some results. Okay. So if your network is strongly connected, there is a Perron eigenvector well-defined, all entries are strictly positive. This is what I would like you to keep from this discussion so far. Fine? And all other eigenvalues are strictly inside the unit circle. And this will be important later because when we study the dynamics of networks, we're going to take this A and introduce its eigendecomposition. When you introduce its you know what eigendecomposition is? Jordan decomposition. You know what Jordan decomposition is, right? Every matrix, you can transform it by similarity transformation to a Jordan blocks, right? You will have Jordan blocks. One of these Jordan blocks will have size 1. The eigenvalue at 1, right? The other Jordan blocks may have size 1 or more than 1, but the important thing, all of their eigenvalues will be inside the unit circle. If you compute powers of A, you can see already which part of A will disappear and which part of A will stay, right? So this is another aspect of this result that we'll be using later in the analysis, okay? Very good. So let's move on, okay? So now I will answer your second question. How do I tell whether the network is connected or not, okay? Okay, so this part of the lecture is based on the appendix I mentioned before, okay? So appendix A, you can download it also from my website, okay? So I talked about strongly connected networks, weighted graphs, right? Primitive matrices, left stochastic matrices, Perron eigenvector. You will hear this a lot in this course, okay? So now how do I tell if I give you a generic network, right? How do you know if it's connected or not, right? Automatically, I mean, of course. If it's a small network, by looking at it, you can tell, but we want to formalize it, right? Is there a procedure, a test that I can run to tell whether a network is connected? But connectedness now means from the perspective of a graph, just whether there is an edge connecting the agents or not, okay? So let me define it for you, okay? So now, I'm just reminding you what the neighborhood of an agent is, okay? This is the notation. The set of all agents that have edges with K, including agent K. And now, this notation here, by the way, I will be using it in these lectures. This is the neighborhood of K, and this is the cardinality of that neighborhood, how many agents you have there. Let's say 3 neighbors plus myself, so n, my n will be 4, right? So n is always larger than or equal to 1 because at least each one of you is in his or her neighborhood, right? So this n is, okay. Now, with every network we can also assign a matrix. So this is different from the combination matrix. This is called the Laplacian matrix, which I'm going to define. It's also n by n, agents by agents, okay? So what is the, again, this particular matrix reflects the graph that connects the agents, not the weighted graph, but the graph itself, okay? And this is how it is defined, okay? As you are going to see, it's a symmetric matrix, and this is how it is defined, okay? So this is your matrix. You have agents 1, 2, 3, 4, 5, and so forth, right? So on the diagonal 1, 1, 2, 2, 3, 3, you are going to put the number of agents, the number of neighbors you have minus yourself, okay? So that's what you're going to put on the diagonal, okay? I'm going to give you an example in the next slide. So the diagonal entries of the Laplacian matrix tell you how many neighbors essentially every agent has. You just add 1 to that element, okay? Okay, and what about the off-diagonal elements? Okay, so for example, if you take the entry KL, okay, KL, it will be 0 or minus 1. 0 or minus 1 depending on whether they are connected or not. That's all. Depending on whether they are connected or not. Okay, so if K and L are neighbors, then you put a minus 1. Now, why do you do this? You're going to see this results in some interesting properties. Because let me give you an example. Let me go to the example and then come back to the other definitions. Here, I have a graph here, okay? This is a graph. How many agents do I have? 6. How many edges? I numbered the edges here. These are not weights. These are number. Okay, number. I have 8. Just to show you that edges and number of agents, right, generally are different. So forget about the edges for now. That's the second matrix I'm going to define. For now, I'm only focused on the agents. I have 6. So the Laplacian will be 6 columns, 6 rows. Okay. What do you put on the diagonal? On the diagonal, you look at every agent. Let's say agent 1. How many neighbors agent 1 has? 3, so you put 2, right? Okay. Okay, you like that, right? Simple mathematics, right? How many neighbors agent 2 has? So you put 3. And that's how you construct the diagonal. Okay, now let's look at any other entry. Let's say this entry here is what? 2, 1, right? 2, 1. Are they connected? So minus 1. 3, 1. Yes. And all the others are 0. Right? Now, you see, why did we put here degree minus 1? Because now if you add these columns, what do you get? You get 0 always. Right? You get 0 always. That's why it's defined like. So this is a property of the Laplacian matrix. All the columns always add up to 0. Yeah.
What if you have a self loop?
No, yeah, okay. This is what I said here. When we define the Laplacian, we don't consider self-loops, okay? So I say it's here. Anyway, it's mentioned somewhere explicitly, okay? So when we define the Laplacian, we just look at the edges, okay? Forget self-loops, okay? We just want to know whether the graph as is connected. Okay, if you can find a path, these are not weighted paths, but if you can find a path linking agents, okay? Okay, so you understand what the Laplacian is? Very soon I'll define properties of the Laplacian for you, okay? Let's define this other matrix first, okay? So you know, okay, so that's the Laplacian, okay? And every column, well, you already know that every column adds up to 0. So let's define now another matrix called the incidence matrix. I denote it by this calligraphic I, okay? L for Laplacian, I for incidence. Now, this matrix takes into account edges and agents. So that it's not a square matrix. So Laplacian is only n by n, it relates to agents. This relates to agents and edges. So how do you define it? Okay, this is how you define it. Okay, so this is your matrix. Okay, the number of rows are agents and the number of columns are edges, right? Okay, so now what you are going to do, every edge, right, every edge, let's say edge 2 here, will connect some 2 agents, right? Let's say 1 to 5, right? Every edge connects 2 agents. You put +1 in one location, -1 in the other location. Where do you put the plus or the minus? This is convention. Usually we put +1 at the lower index node, in this case at 1, and -1 at the higher index node. This is just convention. You can't do it the other way. You understand? Okay. So by looking at the incidence matrix, if you look at the columns, I can tell that edge is connecting which node to which other node. Right? So let's look at the example. Here, this example here. So how many nodes I have? 6. How many edges I have? 8. Right? So let's look at edge 2. Edge 2, this is it. It's connecting 1 to 2. You put 1 and -1. Okay? So let's look at edge 5. Edge 5, here it is. It's connecting 3 and 4. So here it is, 3 and 4. Right? This is how you define the incidence matrix. So by looking at the incidence matrix, you can figure out the graph. Right? By looking at the Laplacian matrix, you can figure out the graph. Who is connected to who, right? Okay, so there is a relation between these matrices. It's not very difficult for you to verify. This is just simple algebra, that this L, the Laplacian, is actually this incidence matrix times itself, the transpose. Simple algebra, right? If you take this times the transpose of this, you are going to get the Laplacian. Simple algebra to do, okay? So from this, you already see that the Laplacian is symmetric and non-negative definite, correct? Right? These are 2 useful properties of the Laplacian, right? It's symmetric, it's non-negative definite. Okay? Therefore, if you introduce the eigenvalues of the Laplacian, how many do you have? N. All of them will be non-negative, correct? So far, very simple. Okay. Let's order them. Let's assume that 1 is the largest, n is the smallest. What is theta n? Remember, I told you that the columns of L add up to 0, right? Doesn't it means this, right? Right? Is this correct? Okay. So every column, no, not like this, transpose, right? Well, it's the same, symmetric, right? Because the columns add up to 0 and the rows add up to 0, right? Yeah, that's true. The columns add up to 0. Yeah, Kun, you're not paying attention today, right? The columns add up to 0 and the rows add up to 0, right? Very good. So L1 is 1, right? 0. 0. Good. So you're paying attention now, good. Okay. So what is theta n? Right? So the Laplacian, the smallest eigenvalue of the Laplacian is always 0. That we know. Right? What about the one next to it? Theta n minus 1. We know all of them are non-negative. The smallest has to be 0 by a construction. What about the next one? This next one has a name. It's called the algebraic connectivity of the network. If it is different from 0, I'm going to prove this. If it is different from 0, your network is connected. Your graph is connected. Okay, I'm going to prove. This requires proof. Okay, so this is one way for you to check whether your graph is connected. Find the second smallest eigenvalue of the Laplacian. If it is positive, it's connected. What if it is 0? Then how many zeros you have? 2. Then your graph will have 2 disconnected subgraphs. If the 0 is repeated 3 times, you will have 3 disconnected subgraphs. So the multiplicity of the 0 here tells you how many disconnected subgraphs you have. This requires proof, okay? So, are you following? Okay. So this statement is just trivial, just algebra, okay? Now, so I'm denoting the eigenvalues of the Laplacian matrix by thetas, and I'm ordering them with theta n denoting the smallest. Now the Laplacian has the following properties, most of which you already know. A, it is symmetric, non-negative, definite, right? Trivial. And therefore the eigenvalues are non-negative, always, right? Very good. The columns add up to 0, okay? So 0 is an eigenvalue. So theta n is always 0, okay? The question is whether this 0 repeats now, okay? So, okay? So the smallest eigenvalue is always 0. The one next to it, we call it algebraic connectivity. That's the name that people used to refer to this second eigenvalue. Just because it tells you how connected that network is. If it is 0, it's not connected. If it is non-zero, it is connected. Okay? And the number of times, so, okay, so this is up to C, we already know, right? The proofs, we already know. So it's D and E that I have to prove. That the number of times that that 0 is repeated is the number of subgraphs you are going to have, okay, that are disconnected. Okay? So if it is 2 times, you have 2 separate subgraphs. If it's 3, okay? That's one. And then, if it is non-zero, the new graph is connected, and actually it is if and only if condition. For the graph to be connected, it's if and only if the algebraic connectivity is non-zero. That's the property, okay? So let's prove it. So I don't need to prove ABC, right? Only D and E, okay? For part D. What's part D? Okay, if. Let's assume I'm going to prove part, okay? Let's assume part E is correct. I'm going to prove it soon, okay? I'm going to prove it soon independent of the others, okay? I'm using E to prove D, and the proof of E is independent of ABCD, okay? Let's assume that you know E, okay? Okay. So assume that your network consists of 2 separate subgraphs, okay? So this is your network you have here and then another subgraph here. They are not connected, right? They are not connected. Okay. When you write down the Laplacian matrix for this graph, right? Remember the Laplacian matrix, you put the degrees on the diagonal, and who you are connected to, you put -1s, right? If you write down the Laplacian for a network that has 2 subgraphs, it will be block diagonal. Just write it down and you will see. It will be block diagonal, okay, because they are disconnected. You will not have any entries linking nodes from here to nodes from here. Then if you look at the Laplacian matrix, when you write it down, when you write the Laplacian matrix for 2 subnetworks like this, you will have something here and something there. Okay, they will be block, it will be block diagonal. This will be an L1, this will be an L2. Just write it down. Write down an example, a simple example you will see. That's what will happen, okay? Okay. Now, if these subgraphs, each one of them has its own Laplacian, if each one of them is connected, this will have a 0 eigenvalue as the smallest one. This will have a 0 eigenvalue as the smallest one. So how many times the 0 is an eigenvalue of L? Twice, right? So if you have 2 separate subgraphs, you will have 2 0 eigenvalues. 3 separate subgraphs, you will have 3 0 eigenvalues, and so forth, right? So the number of 0, the multiplicity of 0 as an eigenvalue tells you how many subgraphs you have. Okay, now, I still need to prove part E, okay? The last part, which is, if theta n minus 1 is different from 0, then your network is connected, your graph is connected. Fine? Okay. Yes.
We have 2 communications classes.
Yes.
It will be the case that one sends information to the other, but not the other way.
No, here, no, yeah. Here, I'm not talking about weighted graphs in this part, right? I'm just talking about graphs. You see, if you go back, I didn't put weights now. Okay, so the Laplacian is is meaningful. Sorry, where is the figure? The Laplacian is meaningful for you to check whether this graph is connected, meaning there are edges. There are no weights here. It's not for weighted graphs, right? This is not what I'm doing. Okay? Fine? Okay. So, now, can be a good homework problem. How do you check whether a weighted graph or an exam problem? The weighted graph that we talked about. Okay. Sorry? Well, that's part of the question, right? Okay. So, anyway, so let's prove the last part, okay? You understand this is for graphs, right? This is what you would see in courses on graph theory. That's what they would focus on, okay? The last part is your graph is connected if and only if the algebraic connectivity is different from 0, correct? And it's if and only if. So let's prove that, okay? So where is that? Okay. So let's prove part E. So let's assume first that the algebraic connectivity is non-zero, okay? Theta n minus 1 is non-zero. Then the graph must be connected. Why? Because if it were disconnected, your Laplacian has to be block diagonal. You have to have at least 2 zero eigenvalues, right? So one direction is obvious, okay? So let's assume, okay, so if your algebraic connectivity is non-zero, the graph has to be connected. Okay, this direction is obvious. Let's do it the other way, okay? Let's assume that the graph now is disconnected, okay? Disconnected, okay? No, sorry, I already proved this. Okay, for the converse statement, right, that's what I said. If your graph, okay, so if the, sorry, okay, I have to prove two directions, right? If this is different from 0, your graph is connected, right? And if your graph is connected, I have to prove that, right? Okay, I have to prove both directions. Okay, now this direction is obvious, the first one. If the algebraic connectivity is non-zero, it has to be connected. Why? By contradiction. If it is disconnected, the Laplacian will be block diagonal, and you will have multiple eigenvalues at 0. This cannot be true. So the first statement is obvious, right? So I want to show now the converse statement, okay? The converse statement. Assume your graph is connected, right? Okay, and let's show that this smallest eigenvalue is non-zero. Second smallest eigenvalue, okay, is non-zero. Now, how do you show that? To show that the second smallest eigenvalue is non-zero, you need to show that the smallest eigenvalue, the 0, 1, has multiplicity 1, right? That's what we have to show, right? That we already know that 0 is an eigenvalue. I have to show that it has multiplicity 1. Okay. Now, I already know that 0 is an eigenvalue because of what I said before, right? By the way, whenever you see red in my slides, it's a typo, right? It's a typo in the notes. I think I had it 1 in the notes, okay? So it's 0. Okay. So, 1 is an eigenvector corresponding to the eigenvalue 0. If I want to show that this eigenvalue 0 has multiplicity 1, what I need to show is that any other eigenvector is a multiple of 1. If I can show that, then 0 has multiplicity 1, correct? Okay? And then I would have shown that if the graph is connected, then the 0 eigenvalue is unique. Okay, so let's show that. Okay? So let's assume that there exists a vector x that satisfies that equation, that you have another eigenvector associated with the eigenvalue at 0. Then obviously if you multiply by x transpose from the left, you also get 0, right? X transpose Lx, you also get 0, right? Now if you write down, this is a quadratic expression in x, just plug in what L is, expand it, just write it, let's say for a 4x4 network, write it down, you will see this is what you get. You will see that this condition tells you that over the neighborhood of k, if you look at these differences squared, they are all 0. That's what this translates into. Remember, this L has -1 entries in it. Now, this is just a small algebra here, which I'm not showing, okay? The small L has -1s in it, has the degrees in it. Just write down these entries, x1, x2, x3, x1, x2, x3, put the entries of L. You are going to see that that equality implies that if you add these differences over every neighborhood, they should be 0. Okay? They should be 0. Okay, now, but this is a square. For it to be 0, xk has to be xl. So you conclude here that over every neighborhood, the x's have to be the same. But since your network is connected, an x that lies here also belongs to another neighborhood. And those x's have to be the same, right? So you see that all the x's across the network have to be the same. So this x has the form some multiple of the vector 1, right? You understand? Did you follow it? Okay. No? Okay, here. From here you get that, you see your vector x has n entries, right? x1, x2, xn. Because it is of the size of the network, right? This condition implies that the x's over. Okay, so let's write down, let's put some topology here. Okay, so this is a topology. Let's say, whatever, this is a topology, okay? So this is 1, 2, 3, 4, 5, 6. Okay, so let's look at the neighborhood of node 5. What is the neighborhood of node 5? 1, 3, 6, and 5, right? This will tell you that x1, x3, x6, and x5 have to be equal, correct? Okay, so x1 has to be x3, has to be x5, has to be x6. Now let's look at the neighborhood of 3. You have 3, 5, 2, and 4. Those x's have to be equal. So x2 is equal to x4 equals to x3 equals to... So if you propagate this argument across the network, you get that all the x's have to be the same. So all the entries of... So this x will be something times the vector 1. Right? So from which you conclude that this 0 eigenvalue has multiplicity 1, and therefore the algebraic connectivity has to be non-zero. Fine? So I proved the lemma. Okay?
Why does a block diagonal matrix have always at least 2? Like, if L is block diagonal, why will it have at least 2 0 eigenvalues?
Because each Laplacian, by definition, has a 0 eigenvalue, right? Yes. Each one of these L's will be a Laplacian in its own right. When your matrix, when your network has 2 subgraphs and you write the capital L, you will observe that it will consist of 2 Laplacians. Each one will be a Laplacian and has a 0 eigenvalue, by definition, right? Okay, so let's move on. So now you understand what networks are, what strongly connected networks are, right? Perron vectors, primitive matrices, Laplacians and incidence matrices, and this algebraic connectivity concept, okay? So now moving forward, now that I have a network, okay, it's easier to explain this discussion here by looking at the figure. Now that I have a network, we want to do something meaningful with the network, right? So from now on, I'm not going to be using 2 arrows going up and down. I'll just use an edge. You see K and L an edge, and there are weights on this edge, meaning that the exchange of information is 2 ways. So now, what we would like to do with these networks is solve some meaningful problem, right? Solve some meaningful problem. So the way we are going to do it is, in general, we are going to have some cost functions or utility functions or risk functions. People use different names depending on the field, right? That's what happens, okay? In the previous course, 210A, we called it risk function when we were talking about learning algorithms, right? And cost functions when we were talking about adaptive algorithms, right? It doesn't matter what the name is. So each agent will have some cost function of some unknown associated with it, right? Some unknown. I'll show you examples, right? And okay, you saw some examples before, but you will see more examples here. Now, these costs do not need to be different, They can all be the same, right? Often we want to minimize the sum of these costs. If all the costs are the same, you are minimizing the cost itself, right? Okay. So you have applications where all agents would like to minimize the same cost. In machine learning applications, that's a common situation. Okay. Or you may have applications where different agents would like to minimize, different agents are associated with different risks, and the network as a whole would like to minimize the aggregate sum of that. Okay, the aggregate sum of that. You will see examples. Okay. So this is my notation for the costs. Okay. And this is my notation for the aggregate cost. Okay. Global just to mean aggregate, okay? It's the sum of the individual costs. And you saw in the lecture on centralized processing, right, that the way to derive, if you have a collection of agents and they are collecting data in the field and they send them back to a centralized processor, one way to develop an algorithm that fuses all that information together is by minimizing an aggregate cost like this, right? Okay. So this is my notation for the aggregate cost. Now, when we studied standalone agents, right, we imposed certain conditions on the, right, when you had an agent on its own, J sub k, trying to minimize some cost, mean square error cost, a logistic error cost, right, we imposed some conditions on the cost. For example, we required it to be strongly convex, meaning it is convex, and the Hessian is sufficiently away from zero, right? The Hessian, the second order derivative, sufficiently away from zero, right? So it has a well-defined unique minimum, right? And we also assume that the Hessian is bounded from above, right? And we saw many examples of interest satisfy these properties naturally. And we used both the lower bound and upper bound in the single agent case to establish conversions, performance results, right? That's what we did in the previous lectures for single agents. We will repeat that for networks, okay? So now, I'm going to continue to assume that the J sub k's are convex functions, okay? You can relax that condition, by the way. You can require only the sum to be convex. But to keep things tractable in this course, because the derivations become more technical if you relax that condition, okay, I'm going to assume that the JKs are convex, okay? It's sufficient to assume that the sum is strongly convex, okay? That's sufficient, which doesn't necessarily need all the JKs to be convex. For example, one JK could be the negative of the other and they cancel each other, and that JK can be a very arbitrary function, right? Okay, but for us here, we are going to assume, and this is very reasonable in many applications, the JKs are convex, and at least one of them is strongly convex, right? Something is convex if the second derivative is non-negative, right? Strongly convex is strictly away from zero, that's okay. If at least one of them is strongly convex, then the Hessian of this will be strictly away from zero, and this will be strongly convex, right? Okay. I will make these conditions more formal later, okay? So like I said before, okay, we are going to assume that the Hessian matrix of this global function, so this is the second order derivative, is bounded from below by nu sub d for distributed, right? I used nu sub c for centralized before, and bounded from above, delta and nu. This h is just the type. If you are dealing with real variables, it's 1. If you are dealing with complex variables, it's 2, like I explained before, right? What matters is that I need the Hessian to be bounded from below, and it is if it is strongly convex, and to be bounded from above. Many problems of interest satisfy these conditions like we saw before, right? So the same conditions will be here. The same conditions you saw before, we will continue to use them, okay? Okay. Now, another thing I would like to mention, because this matrix, this function is strongly convex, it has a unique minimum, right? If you minimize the global cost over omega, it will have some unique, well-defined minimum, and this is my notation for the minimum, always the optimum, right? Very good. Now, before I continue, we will be interested always in minimizing this global function over omega. Find the omega that minimizes it, which is the omega 0 that I just defined, right? Now, if all the j's are the same, all of them are minimizing the same j sub k, it's a common j of omega, then the minimum of that j is the minimum of this j, right? Because it's just n times that j. Okay. So that's a situation where the individual minimum coincides with the global minimum, right? There are other situations where the costs are not necessarily the same, but the minima are still the same. Okay, I'm going to show you. But there are also other situations where the individual minima here do not need to agree among themselves and do not need to agree with the global minimum. That's the more general case, right? The individual costs, each one of them may have a minimum, which I denote by this notation. These could be different among themselves, right? Two different agents, K and L. And they can be also different from this. This can happen. Right? They can be different among themselves, different from the global minimum, or they can be the same among themselves and the same as the global minimum, right? Many situations can occur depending on your problem, right? And these issues will come back. The analysis that we will do will be general. It will capture all these cases together, okay? So let's look at an example. Okay, here I'm just mentioning that you have situations where all of the JKs are the same, where the global minimum need not agree with the local minimum and so forth, okay? Now, situations where all agents are interested in the same minimum are common. For example, in biological networks, if you have a school of fish moving towards a target, a food target, all of them are interested in the same objective, getting to the same W0, right? So situations like this are common in practice. They are not uncommon, okay? Very good. This is an example. Okay, let's assume I have n agents. Each one of them, each agent K, is measuring data that arises from a linear regression model like this, right? So W0 is some channel impulse response sequence, right? U is the regression vector, so at agent K time I, so this is an inner product, it's a scalar, noise. So each agent, let's say this is the output of some FIR filter. This is the impulse response sequence, W0 of the filter. This is the regression data, right, sitting inside the tap delay line. You collect, right? So let's assume that every agent, okay, is measuring data related to some unknown vector like that, okay? And let's assume that every agent would like to estimate that omega 0 by solving a mean square error cost, minimizing a mean square error cost function, right? We saw problems like this a lot, right, before. Okay, you know what the minimum is, right? We know that if you introduce the covariance of U, right, and the cross correlation, okay, I did not define it here, but if you introduce the cross correlation between D and U at node K, right, which is, right, this is the cross correlation between D and U, right, something like that, right? You know that the minimum for this, if you just minimize over omega, right, find the gradient, set it equal to 0, is given by this equation, right? The solution to the normal equations, the covariance inverse, cross correlation, right? This is the solution to the mean square error estimation problem. Of course, this is assuming RU is invertible, okay? So now, every agent, at every location K, you may have different moments, right? And this is if the moments are such that at every location K you get a different WK0, then this is a case where agents are measuring data and they are interested in different minima, right? However, if all the data arise from the same model, if you come to this equation and you multiply from the left by UK star, the conjugate transpose, and take expectations, it is uncorrelated with V, then you will find that RDU K is RU K W0. So you find that W0 satisfies the same normal equations, right? So in this particular case, when you have multiple agents collecting data related to the same model, even though the moments might be different at the different locations, and therefore the cost functions might be different at the different locations, the minima are the same. Right? So this is a problem where all agents are interested in the same minimum, the same unknown channel, right, that gave rise to their data. Right? This is one example, okay? Very good. I have a representation for it here, right? This is the representation. At every location K, you are measuring data coming from an FIR channel like this, right? Or more generally, an inner product like this subject to noise. We know that the unknown satisfies the normal equations. We know that the solution to the mean square error estimation problem satisfies the same normal equations. Therefore, this is a problem where all agents are interested in finding the same omega 0, right? Since this omega 0 minimizes the individual costs, all of them, it will also minimize the global cost, right? And since the global cost is strongly convex and has a unique minimum, then this omega 0 is that unique minimum, right? Understood? Okay, now, observe the following. Right? For you to be able to find the minimum on your own, RUK has to be invertible, right? Because this will come up next. So why, since every agent can solve the problem on its own, why do they need to cooperate? This is one reason. One reason is here. It can solve it on its own if it has enough information. First, it needs to know RDU and RU. In general, they don't know RDU and RU, right? This is the whole concept of adaptation. You don't know the statistics, but you have data that arise from that statistics, right? So they may not know RU and RDU, number one. Number two, even if they knew their individual RUs and RDUs, at a particular location K, the data may be singular, ill-conditioned. You cannot invert it. So others may be able to find the W, but this K will not be able to find the W. However, if they cooperate together, the network will be able to find the W because the Hessian matrix for the network cost is necessarily invertible because we assume that the Hessian is bounded from below away from 0. The sum of the RUs, because you see it is the same W, right? You can put different RUs here, same W, different RUs here. So the sum times the same W is the sum. That sum will be invertible, right? The individual may not be, but the sum will be. So the network will be able to find it. Okay? So that's another reason why you would like to cooperate, because you may not have sufficient information at the local level, but the global may be able to find it. Okay? Okay, and this is just another example similar to that one. If at every location K, you are observing some autoregressive process, and betas are the coefficient that you would like to estimate related to that autoregressive process, you can collect these betas into a vector W, and you can collect the previous D's into a vector U, then this again becomes D equals UW plus noise, and this falls back into the same problem, okay? Okay, falls back into the same problem. Where is it? Okay, here it is, right? Put the D's here, the betas here, you get the linear regression model. Okay, very good. So now, this will be a very important class of networks that I will be using as examples throughout the remaining lectures. I will use other networks as well, but this is one important one, okay, which I represent like this, okay? I call this mean square error network. It's exactly what I just described. You have a collection of agents, each one of them measuring data that comes from a linear regression model, right? And each one of them has a mean square error cost associated with it, and you are interested in minimizing the aggregate cost. So this is called mean square error network, right? Because of the name, because of the cost, right? And so whenever I refer to a mean square error network, I refer to this network, to this kind of network, right? Where it is a linear regression model and mean square error cost. And I assume that the data across the agents satisfy the following properties. The noise across the agents are independent of each other, which is a reasonable condition. And the regressors across the agents are independent of each other, which is a reasonable condition, okay? And that the noise and the regressors are independent of each other, which is also a reasonable condition. I'm not saying this holds always, but these are reasonable conditions, okay? Assume that the data over space, essentially, is they are independent of each other. So the noise here is independent of the noise here. This is the assumption we make for this model, for this example. Why? Because then it makes it easier for us to come up with explicit analytical expressions to characterize fully the performance of networks like this. Okay? So here it is, right? These are the three conditions I mentioned, that the regressors are, the noise are independent. So here it is, this is over, right? K, L, over space and time, you see K, L, I, and J. The same thing here, K, L, I, and J. And then the noise and the regressors are independent of each other, okay? These are similar to the independence conditions that you see frequently in the context of adaptive filters, right? Even though they may not hold in general, right? You can argue that if your step sizes are sufficiently small, like we argue in the context of adaptive filters, the results that you obtain under these conditions are close enough to first order in mu. They agree to first order in the step size with the results that you would get if these conditions do not hold. Okay? So this is a class of networks that I will be using, okay, a lot. So, and then I come back to the question I mentioned before. Okay, so why do we want to cooperate? We want to cooperate for the following reasons. First of all, agents may not have full information about the moments they need to determine omega 0. They may not know the moments. Right? That's the main reason why we want to develop adaptive algorithms and learning algorithms. We don't know the cost functions, because the cost functions are expectations of some random variables, expectation of a loss. And to determine the expectation of the loss, you need to know the distribution of the data, which we don't know. Okay, so this is one big reason, right? The second reason is that you are observing data, and different agents will be subject to different noise conditions at their location. Some data will be noisier than other data, and you saw this in the lecture on non-cooperative agents, right? Some agents will see different signal-to-noise ratio conditions than other agents. So if they work on their own, there is a limit to what they can achieve. But if they work together, right, they can equalize their performance, right, and improve their performance. We are going to prove that. You saw an example of this when we studied non-cooperative and centralized solutions. Right? Here you will see it later in the context of networks. I'm going to prove these facts, okay? The other reason why you want to cooperate, okay, is that, like I said before, the individual costs may not be strongly convex. For example, one particular RUK may be singular. So this is the Hessian matrix of that particular J of K in the mean square error case, right? But more generally, the individual costs, not all of them need to be strongly convex, and therefore if you work on your own, you may not be able to find the minimum that you are looking for. You have to work with the others to be able to find it, okay? And even if each one of them can find it on their own, as you are going to see, just like happened with centralized processing, even if each one of them can find it on their own, if they work together, they can improve their performance, right? This is what we are going to show later, okay? So to summarize, okay, so these are the key points that I want you to remember from this lecture, right? So today I spent time talking about the network model, okay? I introduced a strongly connected network. You have a weighted path with non-zero weights between any two agents in any direction, and at least one self loop, right? So this is what a strongly connected network is. And then if you introduce the combination matrix n by n that represents that matrix, that network, it will be left stochastic. Each column adds up to 1. The A's are non-negative, they add up to 1. Left stochastic. Not only that, it will be primitive. You can find an N0. We don't really care much about this result. We care more about the consequence that follows from this result, that there exists this Perron vector, right? It will be a primitive matrix, meaning there is an N0 that makes all entries positive, but more importantly, it follows from that A will have a single eigenvalue at 1, all other eigenvalues inside the unit circle, and we can pick a particular eigenvector normalized to add up to 1, whose entries will all be positive. This is called the Perron eigenvector. It will be very important for us. Later, for example, we are going to discover If I give you, and I asked you this question before, if I give you two different I have n agents, there are many different ways by which I can connect them, right? And many different ways by which I can pick the combination weights, right? So many ways by which I can pick A for a particular collection of agents. Okay? How do you know which network will perform better? Right? Which topology to choose? What matters about A? What matters about A, you're going to see later, is this P. The P. If these two different topologies have the same P, then the performance expressions essentially will be the same. Okay, it is this P that will summarize the effect of the topology on performance. Okay, that's why I introduced it. But this, I need to qualify this statement, and you will understand it more rigorously later. Okay? And then we are interested in solving an aggregate cost optimization problem like this. I want to minimize the aggregate sum of individual costs. One particular example is the mean square error network, but there are other networks, okay? Logistic regression will be one example, right, for example, and many others, okay? And why cooperate? I explained, right? Agents will be subject to different amounts of noise. They may not have sufficient information to know their individual cost function, and even if they have sufficient information, that information may be ambiguous, right? May be singular, ill-conditioned, and so forth, okay? End. So do you have any questions? That's what I wanted to share with you today. Explain the network model in some detail so that from the next time onwards we can start talking about algorithms now over these networks, okay? But keep in mind that these networks can be very sparse, even though the figures I showed you shows many connections, but think of bigger networks where the connections are sparse, okay? Any questions? You understood the main ideas? Yes.
So we started with the assumption of having bidirectional links
Yes.
between nodes.
Yes.
Can these algorithms generalize to networks who are directed?
Well, you can, but the performance you are going to get will be different, because one of the consequences that will follow from the fact that you have this bidirectional flow of information is that you can equalize the performance across all agents, right? If now you have a structure where, for example, information never arrives at a particular node, you cannot get the performance of this node to be similar to the performance of the other nodes that are seeing other aspects of the information. You understand? Okay, so that's what will happen. Okay, you will not be able to equalize performance across the network, but you can follow the analysis and derive expressions. Okay? Good? Okay, so let's stop here. We'll continue next time. Okay?